All right, so now we're on radicals lesson 5, and this is radical equations. So we're going to take our knowledge of what a radical is, and now we're going to apply it, whether it's graphing or solving for specific solutions, in what we're going to call radical equations or expressions. So let's consider the following here. What if I have the radical root x? Well, we know every radical must be greater than or equal to 0. Reason being is that we cannot have a negative radical here, or a negative square root. This does not exist. So now let's see how this works in our example. On the grid, let's sketch the graph of this. If we know x must be greater than or equal to 0, well, I'm going to plug in x as 0. So if x is 0, we get square root of 0, and that's our first value here. If x equals 1, that's the square root of 1, which is 1. If we do 4, x equals 4, that's the square root of 4. That means we would have a value of 2. And what you would actually notice about this graph is it's going to kind of taper off like this and become really flat, but extend out infinitely in the x and y directions here. Now, when they say state the domain of this, we know it relates to all the x values. Well, x such that x, what did x have to be greater than? 0 in this case. X was greater than or equal to 0, and once it was past 0, it was an element of the reals. And we can throw on our curly brackets here for formal notation. However, it is not required as long as you can get that x is greater than 0 and x is an element of the reals. Now, for what values is this radical expression defined? Well, we knew it was when x was greater than or equal to 0, because we cannot have a negative radical. Now let's apply the same thing to part B. On the radical expression here, let's do a grid or a graph of this. So I'm going to start plugging in points here. If I have x is equal to, remember, this radical cannot be negative, meaning I have to look at this and say, if I start plugging in things like x equals 0, that's going to leave behind just that negative 2. And if I have a square root of negative 2, that does not exist. So I'm going to start by plugging in x equals 2. When x equals 2, we get 2 minus 2, and that's 0. When I put in x is 3, 3 minus 2 is 1, square root of 1 is 1. So we have 2, and then continuing onwards. And now I could throw in something like, what if I had x equals 6 minus 2? Well, that's the square root of 4. Therefore, I would get a point at 6 and 2. And now I could draw out my graph and continue it, and we know it extends out infinitely in the x positive direction and the y direction. So when we go to the state the domain, well, in this case, in order for the radical to not be 0, it had to be x such that x was greater than or equal to 2, and once it was past 2, it became an element of the reals, or any possible value. What are the restrictions? Well, we just actually expressed it in the domain. It must be greater than or equal to 2. How can we solve these algebraically? We take everything in the radicand position. So we take the radicand, or everything under the root, and we set it greater than or equal to 0. If we take everything in the radicand and set it greater than or equal to 0, this is really easy. X minus 2 is greater than or equal to 0. I solve this, which moves the 2 across. I have x is greater than or equal to 2. So we've shown that if we take our radicand and set it greater than or equal to 0, we can get our restrictions algebraically. Now, for example C, I'm going to let you do that one on your own. It follows the exact same principles. You'll be asked for the restriction, the domain, but that is one I would like you to try. Now, let's note this. Radical expressions involving square roots may have restrictions on the value of the variable because the square root of a negative number is not defined. Hence, why we have restrictions, because radical expressions cannot be a negative number because that is not defined. So that was the point above why we set them greater than or equal to 0. It cannot be a negative number because it's not defined. Now, what if we want to look at more examples revolving around making radical equations with restrictions that we can find algebraically? So, radical equation is an equation which contains a radical. A value of a variable which satisfies this equation is called a root of the equation. All right, And we know from previous unit, a root actually refers to the x-intercepts. So we could fill this in here. It's the x-intercepts. Now let's actually follow the class example here and see if we can figure out there any restrictions on this domain or restrictions on the x in these equations. So if we want to come up with the restrictions for these, remember we have to take the radicand. In this case, our radicand is equal to x minus 2, and we need to set it greater than or equal to 0. I add the 2 across both sides, and I'm going to get x is greater than or equal to positive 2. If I take my next one, I take all the radicand and go 4x plus 1 must be greater than or equal to 0. I start by subtracting my 1 across the equals sign and finally dividing by my 4. X must be greater than or equal to negative 1/4. Let's go to my next example here. What if I take my radicand here? I go 2 minus 5x must be greater than or equal to 0. I add, let's say, my negative 5x across, so this would become 2 is greater than or equal to 5x. I divide by my 5, x is less than or equal to 2/5. I go to my last example here, and I'm going to take the radicand here. Now, is there really a restriction on the domain? We would ask here, and we would say, is it possible that a cube root can also be negative? That is true here. So we know that when we see the cube root out front here, or the cube, this is going to say that can we have a negative under the radical? We actually can. In this case, there is no restriction or no direct restriction to the radical. All right, another graphing equation. If I look at the radical equation, square root of x plus 1 is equal to 4. State the values of x which the radical is defined. We need to start by looking at x plus 1 must be greater than or equal to 0, meaning x must be greater than or equal to negative 1 when we move the positive 1 across. So we have our restrictions defined where x must be greater than or equal to negative 1. Explain how to use the graphing calculator to find the solutions of this. We can actually do this quite simply. In y1, or the first entry in your graphing mode, you are going to type in the function x plus 1. In y2, you're going to type in 4. So it's going to graph the x plus 1 square rooted, and y2 would be the 4. If I look at this on a graph, it is going to look like the following. And I'm going to use different colors to represent different sections. So our y1 is going to be represented by red, and my y2 is going to be represented by orange. Well, right away, if y is equal to 4, that means I actually have a line directly across where y is equal to 4. That's what that is saying. We have a y equal to 4. Now I need to put together my other function here, or the square root of x plus 1. We know it has to be greater than or equal to negative 1 for this to be true. So if I start by putting in negative 1, negative 1 plus 1 is 0, and the square root of 0 is just 0 here. If I put in x equals 0, well, that's the square root of 1. Square root of 1 is just 1. If I put in, let's say, x equals 3, if I go over to x equals 3, 3 plus 1 is 4, and the square root of 4 is 2. So we can put a point here. And now let me put in some higher number here. So what if I say that I have x is equal to, let's try and put in 8. If I put in x is equal to 8, that means I have 8 plus 1. 8 plus 1 is 9. Square root of 9 is going to be equal to 3. So I go over to where I had 8. In this case, 8 is here. I plug that in, and I found that the square root gave me 3. So I'm going to go up to 3 here. Now I'm going to try something even larger here. I'm going to say, what if I do x is equal to 15? So if I go to x equals 15, well, 15 is here, but my point's not there. I go 15 plus 1, square root of 16 is equal to 4. Now, here's what happens in the graph. It starts at x equals -1 and continues through upwards and upwards and upwards until it intersects and starts flattening out. We have an intersection point at 4. And this should make sense because we said the red graph, or the 1 in y1, should be equal to that 4 or the y2. So we get this nice crossover point right at y is equal to 4. All right, so we could do this on our graphing calculator, which in part B, they wanted us to do this. So we take y1, y2. On your TI, you can actually do second, trace, and then intersect. On the Casio, you can graph these, and then you can go into shift, Gsolve, and then you can click intersect, which I believe it short forms as the following. And I should correct this order, it's int. So we have our TI and our Casio instructions. Now, we could do this in our graphing calculators and use the following window, state the solution algebraic, or state the solution to the equation. Well, the solution is saying what x value makes this true. We actually just found it above here. It's when x is equal to 15. However, if we wanted to do this graphically, we could figure out, okay, where does this intersect? And we could click the intersect just as we had done in the TI above here, second trace intersect, or shift Gsolve intersect. Let's verify the solution algebraically. So verifying this algebraically, I go the square root of x plus 1 must be equal to 4. If I plug in 15 for x, this is equal to 4. Square root of 16 is equal to 4. Is that true? It is. Square root of 16 is 4 is equal to 4. So yes, we can verify this solution algebraically by plugging in that x value that made this true. All right, now an investigation on solving these. So what if I want to solve these algebraically and then verify the solution here, or plug back in that x? Well, to do this algebraically, what they do is they take this original equation of x squared, or square root of x plus 1 equals 4, and to solve it algebraically, we know to undo a square root, we have to square it. So we square both sides, leaving us with, in this case, x plus 1 is equal to 14 square, or 4 squared is equal to 16. Now, if I subtract 1 from both sides, this gives me x is equal to 16 minus 1, or 15. Now, just as we had done before, we can verify the solution by going back to the original equation and going 15, or x plus 1 is equal to 4, and making sure that the left side is square rooted. Square root of 15 plus 1, which is equal to 16, is equal to 4. And then square root of 16 is 4, which is equal to 4. So we have therefore verified. This is a very key word. When they say verify, they want you to take that x value and plug it back in. So the method of solving a radical equation by squaring both sides of the equation needs to be studied in more detail, which we will do in the below example here. So now let's take another example. Let's use the same kind of steps that we did before, but now include another number on top of that. So what we do is we want to isolate for the radical term, or whatever the square root or cube root is. So what we're going to do originally is we're going to say, I'm going to subtract away this 3, subtract away this 3, giving me that next line where the radical is isolated. We then replicate the step from the previous problem and we square both sides to get rid of the radical. And now we can take this from here. X minus 1, because our square and our square root cancel, is equal to x minus 3 times x minus 3, or x minus 3 squared. I get x minus 1 is equal to, and now I can FOIL this, x squared, or x times x. X times a negative 3 is negative 3x. Negative 3 times x is negative 3x. And then finally, negative 3 times 3 is a positive 9. I have x minus 1 is equal to x squared minus 6x plus 9. And now I always want to try and keep my x squared term positive. So if this is positive on this side, I'm going to leave it there and take everything from the left and move it to the right. 0 is equal to x squared. If I subtract away an x and I add the 1 to this side, I'm going to do the same thing to the right and go negative x plus 1. That's undoing everything on the left-hand side and canceling it and leaving me with just a 0. And now I have x squared, negative 6x minus x is negative 7x, 9 plus a 1, that's equal to 10. Now, from quadratic equations, what did we do in this case? We factored it. X squared, we need to multiply to make a positive 10, add to make a negative 7. That's negative 5, negative 2. We know decomposition isn't required because the a value here is 1. So I can go x minus 5, x plus or minus 2, I should say. When I solve these like I did in quadratic equations, I set them each equal to 0 and solve. X minus 5 is equal to 0, x minus 2 is equal to 0. Therefore, x is equal to 5 and x is equal to 2. Now, we have to verify the solutions. This very key word out front, verify the solutions, meaning I have to go to my original equation, the original equation of 3 plus the square root of x minus 1 equals x, and see that this works for both numbers. So I'm going to start with 5. X plus the square root. Let's confirm our function. X minus 1, or 5 minus 1, is equal to, in this case on the other side, x, which was 5. And this should be a 3 out front. Well, 3 plus the square root of 5 minus 1, square root of 4, that's 2, is equal to 5. Yes, 5 does equal 5. We're all set. So we've confirmed that our x equals 5 is a solution that works. We've verified it. Now we have to do the same thing with the x equals 2. I go 3 plus the square root of 2 minus 1 is equal to 5. 3 plus the square root of 1 is equal to 5. Therefore, this is 3 plus 1 is equal to 5. That's like saying 4 is equal to 5. Is that true? Definitely not. So what we've found is that one of these numbers does not work. We verified that one works and one doesn't. Now, we can confirm this graphically, just as we had done before. So what we could do is to do this graphically, I could assign one side equal to y1, or my left side. On the right-hand side, I could go, this is equal to, and I'm going to use a different color, this is y2, and I could solve that graphically to confirm this. All right, so in the investigation number 2, one of the solutions can be verified. One of the solutions could be, but the other verification could not work. We found that one was 4 equals 5 and the other was 5 equals 5, meaning only one of the numbers worked. So here's where we introduced an extraneous root or an extraneous solution. In the previous problem, we recognized that one solution worked and one didn't. So when we verify in any given problem, if we find a value that does not satisfy the original equation, this is called the extraneous solution or extraneous root. Now, a couple notes here. It's always necessary to verify the solution. It is always necessary to verify the solution because it can be solved with a couple different ways. Or we can get more than one x value. And then finally, there will not be an extraneous root with a radical equation where the radical has an index of 3. Why is that? Well, we know that when there is a radical of an index 3, it can have a negative value. So unlike when we square, a cube root can be negative, and it does exist. So there's not the same amount of restrictions, or there's not the same restrictions in regards to ones with an index of 3. And additionally, what I should add here is that each one with an index of 3 has a unique cube root, meaning there's not more than one value. All right, complete the work for the following and determine the extraneous root of the equation. Square root of x plus 2 equals x. All right, so if I look at this, they started off by squaring both sides. This is the correct step. Once we square both sides, we realize the square root and the square cancel to leave me with x plus 2, which is equal to x squared, which is x squared. Now, I keep this x squared positive because if it has a positive coefficient, I'm going to leave it here, and I'm going to move everything from the left over. Minus x minus 2 minus x minus 2. This is 0 is equal to x squared minus x minus 2. Now I can factor this. If I factor this, I have to multiply to make negative 2, add to make negative 1. Well, what's going to do that for me? It's negative 2 and a positive 1. And we do not need decomposition because we know that the a value is 1, or the x squared coefficient is 1. X minus 2, x plus 1. We solve this for the x values. X minus 2 is equal to 0. X plus 1 is equal to 0. I isolate both sides. X equals positive 2, and then x equals negative 1. So I move the numbers across. We did this in quadratic equations. Now, I have two possible solutions. What do I have to do? I have to verify that they're true. So off to the side here, what you can do is you can verify. So to verify, I'm going to plug in x equals 2. I have 2 plus 2, or the x value being 2. I plug that in, and this is equal to 2. 2 plus 2 is the square root of 4, which is equal to 2. And then the square root of 4 is 2, which is equal to 2. So yes, we have verified that x equals 2 is a proper solution for this. Now let's do that with the second one. We have an x this time of negative 1, and it's being added to 2, which is supposed to be equal to negative 1. Negative 1 plus 2 is the square root of positive 1, which is equal to negative 1. 1 does not equal negative 1. Therefore, we verified that this is an extraneous solution. So what you need to do now with these is say, this is an extraneous solution, cross it out, and write ext with it. Cross it out, write ext, and make sure to algebraically show that you verified these are true, like I did off to the right here. So we get one possible solution, or one possible root of the equation. All right, now let's formalize this a lot. So using the following method, we can solve for all indexes of 2. So we're going to isolate the radical term, square both sides, solve the equation like we did in quadratic equations, and then verify the answers because there may be an extraneous root at the end. So let's do a couple examples here. If I do the square root of x plus 3 equals 7, well, step 1 is actually taken care of. Both sides have actually been isolated for the radical. Now, I want to take this and square both sides. X plus 3 is equal to 7. I'm trying to undo the square root and isolate for the x. So I have x plus 3 is equal to 49. Remember, I'm trying to keep the x positive, but I also want to have it isolated. So I'm going to subtract away 3, subtract away 3. Therefore, x is equal to 49 minus 3, which is 46. Now, we have to verify that this is true. That's our last step. So if that's my x value, well, the square root of 46, or x plus 3, is equal to 7. That's the square root of 49 is equal to 7. Therefore, square root of 49 is 7 equals 7. Yes, we have verified that this is a proper solution to this radical equation or radical expression. All right, let's do B here. Remember, the first step is to always isolate the radical. So I'm going to subtract away 7, subtract away 7. Square root of 49 minus x is equal to x minus 7. Now, I need to square both sides. I'm going to put both as squared, or put brackets around everything on both sides and square. We know a square and a square root are going to undo each other, leaving me with 49 minus x is equal to x minus 7 times x minus 7, or that binomial squared. 49 minus x is equal to, if I distribute this, x times x is x squared, negative 7 times x is negative 7, negative 7 times x is negative 7, and 7x, and then negative 7 times negative 7 is positive 49. Now, I have 49 is minus x is equal to x squared minus 14x plus 49. What I want to do here is I want to take everything from the side that, if this we know is a positive here for our squared term, leave this here and let's subtract everything from the left. Minus 49 plus x minus 49 plus x. So now I have 0 is equal to x squared minus 14x, or in this case, we need to make sure we're adding that x. So negative 14x plus the x gives me negative 13x. And then 49 minus 49 just gives me 0. Now I need to figure out what my x values are. I factor this. I can factor out 0 is equal to, and x factors out, and I'm left with x minus 13. And when I isolate for each of these equal to 0, I get x is equal to 0 and x is equal to 13. So we need to confirm which of these are true. And maybe I'm going to show this in a more full way here. So I'm going to continue this above. So I have x equals 0, and then x is minus 13 is equal to 0, x is equal to 13. So those are our two possible solutions here. We need to confirm them. If I plug in a 0, well, the square root of 49 minus 0 plus 7 equals, what is the x value? 0. So we have square root of 49 minus 0, or square root of 49, that's 7, plus a 7 is equal to 0. Does 14 equal 0? Definitely not. So this is not a solution. We know that now we can go back to our x equals 0, cross it out, and write extraneous. Now I need to test my x equals 13. What will most likely happen is if you find one to be extraneous, the other one will work, but let's confirm it. Square root of 49 minus 13 plus 7 must be equal to 13. If I do 49 minus 13, well, that's going to be equal to 36. And 36 square rooted will equal 6. So we get 6 plus 7 is equal to 13. Is this true? Yes, 13 does equal 13. So we have algebraically verified that x equals 13 is a solution to this. And therefore, we got our one answer, or our one root to this equation or expression. Now, it's really important to recap the steps here. We take it and isolate for the radical. So we isolated our square root 49 minus x by subtracting away 7 to both sides. We then said, let's FOIL this out. Or no, before that, we then said we need to now square both sides. When we square both sides, we FOIL one side or expand the side. And we want to keep our x squared positive, so we isolate everything on one side like we did in quadratic equations. We solve it by factoring like we did in quadratic equations, and then we have to make sure we verify. So it's a 4-step solution there as written above, and we just want to accurately follow isolating, squaring, solving, and verifying, because that will be how we do it for all of the problems. Now, we use the same kind of concept, but now instead we're going to move to things with an index of 3, or cube rooting. So we're going to isolate the radical term, cube both sides of the equation, solve, and then although extraneous roots will not occur because the index is 3, we do want to make sure we verify just to make sure that we're doing the accurate work here. Because if we get something that doesn't equal, we know we maybe did something wrong along the way here. So let's solve and verify. Remember, in order to solve, we have to isolate our radical, or in this case, the cube root. Cube root of 2x minus 7 is equal to, I'm going to add the 5 to both sides. Add 5, this is equal to 5. Now, I have to cube both sides, so I'm going to surround everything on both sides in brackets and cube. I get the cube root, or the the cube of a cube root on this left-hand side, those are going to cancel away, and I'm left with 2x minus 7. This is equal to 5 cubed, which is 125. And now I'm going to go 2x is equal to, I add 7 to both sides. 125 plus a 7 will give me 132. And now I divide both sides by 2 to isolate x. Therefore, x is equal to, well, 132 divided by 2 is so therefore 132 divided by 2 is 66. So we get an x value of 66. Let's confirm that this is true by verifying. So I go the cube root of 2x, which is 66, minus 7, minus 5 must be equal to 0. The cube root of 132 minus 7 minus 5 should be equal to 0. The cube root of 125 minus 5 is equal to 0. 5 minus 5 is equal to 0. Yes, that is true. We have verified that this x being 66 does satisfy the equation and is a root of this equation. All right, now it's on to you for the assignment.